Welcome back. In this part of Lesson 8, we're going to talk about the two-path test for non-existence of a multivariable limit. The two-path test comes from the intuition that if a limit exists, the output values should converge to that limit regardless of how the input approaches the point A, B in the domain. Formally speaking, the two-path test for non-existence of a limit reads as follows. If a multivariable function f of x approaches two different values in the range, as the input x comma y approaches ab along two different paths in the domain, then we say that the limit as xy approaches ab of f of x, y does not exist. This outline is available for you in the Lesson 8 handout posted on our course website. Remember that in order for a limit to exist, the output values of f of xy should get arbitrarily close to L as xy approaches AB, and we've said many times that this should never depend on the path on which x and y travels to get closer to AB. In this M1C class, we're not going to spend a ton of time with limits, but we will have a brief introduction so that as we do partial derivatives, you will feel at least somewhat comfortable with the techniques that we're using to find the derivatives using the limit. So in this brief introduction, we will focus on 5 different paths to help determine if a limit may or may not exist. The paths that we will focus on are as follows. First, when we're trying to find the limit, we might assume that the y value is constant, held constant at b, and that instead we just focus on the x values by moving along the x towards a distance, where y equals b is this line, right? So it's a horizontal line in the domain through the point AB, and then literally we've turned a 2-variable limit into a 1-variable limit. The next path that we're going to focus on is the same concept. We turn a 2-variable limit into a 1-variable limit by holding the a value constant and letting y go to b. So this path is along the line x equal to a. And then a third path that we're going to look at is along any line with slope m. So in this case, we look at values of x comma y going to ab, where the y value is given by m times x minus a plus b. Notice this is the point slope form of a line for a general slope m, and then the point a comma b. So this is any line. The slope of this line is 0. The slope of this line is undefined, and then we could test it along any line with general slope m. Finally, the last 2 paths that we're going to try, or that we may try if those 3 don't produce any useful information, are parabolic paths. So the 4th path is going to be a parabola in x through the point AB, where the y coordinate of my point moves towards, is this parabola. It's the parabola x minus a squared plus b. This is a parabola that points upward in y that goes to the point AB. And so we might move towards the point AB along that parabola. We can also test along parabola in y. So instead of the x values determining the y values, we flip it. The y values would determine the x values. And this is basically a sideways pointing parabola. These 5 paths can, in this class, give us some useful information. If we were to test a given multivariable function that we want to take the limit of along all these 5 paths, and we get the same limiting value along all of these, we might conclude that the limit exists and that the value that we're getting is that limit. However, if we try a multivariable function along 2 or 3 of these paths and we get 2 different values, we immediately know via the 2-path test that the limit cannot exist at a given input point a comma b. With this said, let's take a look at our first example here. In this example, we're going to try to show that the limit as xy approaches 0, 0 of the function x squared minus y squared over x squared plus y squared does not exist. Before we actually begin this, I've written some here because I've gotten feedback from you all that I shouldn't write live during a video. So I try to write a little bit beforehand. But before we actually would do this, I would actually look at this multivariable function and test real quick. If I put in 0, 0, does this thing actually evaluate? Is this continuous? 0 minus 0 divided by 0 minus 0, that's non-existent. Also, if we try to do the limit laws there, if we try to bring the limit on the top and the bottom, the limit of the denominator would be 0, and the quotient rule does not apply. The quotient rule of limit does not apply if the limit of the bottom is 0. We're not sure what this limit would be, but we do know if we can find 2 different paths where the input xy approaches 0, 0, and along those paths the output f of xy approaches 2 different values, we know this limit wouldn't exist. By the problem statement, we're given that the limit shouldn't exist, and so we might imagine, well, how could we confirm that? Remember, we just went through 5 different paths that we can test, so let's test with path 1, which was to set y equal to b, and in this case the b value is 0. Okay, so when we look at the limit, instead of x comma y, we're going to take x comma 0 towards 0, 0, so y stays constant, and then we look at x squared minus y squared over x squared plus y squared. And the really nice thing about holding the y constant at 0 is these values become 0, and indeed we've just turned a multivariable limit into a single variable limit. And that's one of the nice things about going along paths. We turn a multivariable calculus problem into a single variable calculus problem. Do you remember what this limit was? Yeah, this limit was equal to 1. So this was the number 1. So along the path y equals 0, we get a number 1, and that was just literally taking the first path that kind of looked like a Pokemon ball, didn't it? Collect them all. Okay. Let's try path 2, just for giggles. Hee 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 hee. When we take the limit as x stays constant and y goes towards 0, we get the same idea of transforming a multivariable limit into a single variable limit. Here, since the x's are not constant, they go away, and I'm just left with y approaching 0, and this would be negative y squared over y squared, but we see via math 1a that that's equal to negative 1. And this one was quite quick. Just by testing those first 2 paths, we got 2 different values, and by the 2-path test, this limit, DNE, does not exist. Boom. All done with that problem. In the next video, we'll take a look at a multivariable function that doesn't yield as easily to paths 1 and 2 and requires some subtle analysis using paths 3 or 4 or 5. Dun dun dun. See you in the next video.